lectures on Chapter 3, focusing on non-covalent interactions. So, by and large, the most important solvent for non-covalent interactions and thinking about biology is water. And so it's useful just at the beginning to consider some principles about solvent and how it can affect these interactions. Here is sort of some graphs that I drew based on what was in your text. This G here represents the probability of a certain spot being occupied. And on the x-axis is distance from your starting point. And so if you're in a crystal and you choose one atom as a starting point, in a crystal you can expect regular intervals where there's a high probability of another atom being. And so this is sort of long-range order, whereas in liquids, if this is, again, distance from a solute, you expect to see a large number of solvent molecules very close to the solute, and then perhaps a second group of molecules near the solute. And I guess I should point out this G term represents order. So the solvent molecules immediately near a solute are more ordered, then there's sort of a second shell and a third shell, and beyond that there's sort of randomness. So when you're thinking about a molecule in water, you need to think of it as being surrounded by a first solvent shell, which is relatively ordered, a second solvent shell that's less ordered, and a third solvent shell that's even less ordered. And beyond that, then the structure of water is sort of bulk and random. So we want to talk about, we're going to talk about non-covalent interactions, but in order to rationalize how solvent and environment impacts those interactions, we're going to go back to Coulomb's law. And Coulomb's law describes the energy of an interaction between two charges. So basically it's going to describe the energy of an electrostatic interaction. Between 2 point charges. All right, so the energy, and this is potential energy, the potential energy of interaction between two charges is equal to charge 1 times charge 2. These are in units of coulombs. You don't need to worry about that. But basically, they come in. We're going to continue to think about +1 charge, +2 charge in terms of the charge of an electron. And then in the denominator, you've got 4 pi. Then you have Greek letter epsilon. Then you have Greek letter epsilon with the subscript. And then you have r. Okay, so charge 1, charge 2. R is the distance between the two charges. Pi is the number. Let's talk about what these epsilons mean. This epsilon here is called the permittivity of a vacuum, and it basically describes how responsive a vacuum is to an electric field. And then the other E is called, let's see, the other epsilon, so this is vacuum permittivity. And I don't totally understand what that means, but the other epsilon is called dielectric constant. And this basically says relative to a vacuum, the dielectric constant equals the permittivity of whatever medium you have, medium X, divided by the permittivity of a vacuum. So it tells you relative to a vacuum how responsive is the medium or the space between the two charges to an electric field. So if we look at this, and by so you can think of interactions between charges as occurring in a vacuum, or you can think about them as occurring in solvent. The idea is if the solvent that's between the two charges is more responsive to an electric field than a vacuum, this number increases. If we increase the number of the denominator, that ought to decrease the number, the energy of the interaction. So that's an important trend. We increase dielectric constant, we decrease the energy of the interaction. And this is an important point because perhaps in general chemistry, you were told that ionic bonds are really strong, right? And, you know, strength is always relative to what? So yes, it is true that you have to heat sodium chloride up a lot before it melts. And yet, you put it in water and it dissolves, right? The reason it can dissolve in water is because the dielectric constant of water is large enough. Water is very responsive to an electric field because it's polar. The dielectric constant of water is large enough that it decreases the energy of interaction between charges, and that's actually easily replaced by interactions between the charge and the nearby water molecules. So organic chemists have a decent feel for what dielectric constant is. There's a table here that's not worth memorizing, but it does sort of rank solvents in polarity. And you probably already know some of this, but or you've already developed some intuition as to what's polar versus not. But water is one of the most polar solvents you can get. So 78 times more responsive to an electric field than a vacuum is. You have other solvents in this list. They include polar but non-protic solvents like DMSO, DMF, acetonitrile. These are often used as solvents in reactions where you're going to have ions, like SN2 reactions. DMSO is very popular for that. Let's see, ethanol is a protic solvent. Acetone is more polar, say, than hexane, but way less polar than water. And so this is sort of a scale you can go down, but when you do flash columns for chromatography, you're usually going to have some mixture of a nonpolar solvent, perhaps hexanes, perhaps dichloromethane or chloroform, and then some slightly more polar solvent, for example, ethyl acetate, or if you need quite a bit more polar, methanol can work.
So, can you talk about
Formamide?
Yeah.
Yeah, what is that? That's just, I don't actually know, I've never worked with this. Formamide, I think, would be this.
Why is it so high?
Probably because of its polarity. You have a dipole aligned this way and that way. So, yeah, my guess is that the dipole is just really large.
Is that the used for reaction?
Do we use formamide? I've never used it. I've used DMF, which is dimethyl formamide. You replace these two with methyl groups. Yeah. All right, there are other solvent scales. I don't know necessarily where all of these are coming from, and in some cases the order changes. On the Z solvent scale, whatever that is, water beats formamide. we won't worry about really any of these numbers other than the dielectric constant. But you may encounter some of these somewhere else. Physical organic chemists love to develop numbers that represent how polar something is versus not, or can tell you, give you a prediction for which way a reaction should go. Okay, so just remember the high dielectric constants have high polarity. They usually have bonds between carbon or hydrogen and electronegative atoms. And they are good at solvating charges, and they decrease the strength of electrostatic interactions. So why is that important? Well, I mean, first, it's the demonstration that ionic interactions can be strong, but you also need to think about context. So as an example, and if we've already started talking about non-covalent interactions. By this we mean energetically favorable interactions that aren't covalent bonds. And the first would be, we'll maybe call it ion pairs. And let's see. In an ion pair, the ions are close enough to each other that the Coulomb's law attraction between the two ions is larger than the available thermal energy that could separate them. And we've just talked about how if you increase the dielectric constant of the solvent, you're going to decrease the presence of ion pairs, which is why, again, water dissolves ions. Let's talk about how context can affect the strength of ion pairs. For example, sodium acetate is what we call a strong electrolyte because in water there's not really any ion pairs, but rather the two ions separate from each other. And the reason for that is that if you add water, you can have water molecules surrounding the negative charge. I'm not going to be able to draw this quickly, but the idea is, oh, and by the way, this symbol is a symbol for a dipole. The little cross here represents the positive end of the dipole, and the arrow represents the negative end of the dipole. So what I'm trying to communicate, though I'm doing so poorly, is that you can have a group of water molecules that surround a solute, and they can align their dipoles such that they interact with the solute and totally replace the interaction that the ion sodium had with the solute. And same thing with sodium. We could similarly, for sodium it would be the oxygens sort of oriented towards the sodium ion. Because in water it's the oxygens that have the partial negative charge on them. Okay, similar sort of thing, a shell of water molecules around sodium. So this would be a separated ion pair, or not even an ion pair. This would be solvated ions. Now, in contrast, you can take the same functional group and put a lot of carboxylic acids into close proximity. I think what I'm drawing here is a polymer called polyacrylate. And because of the presence of all of these negatively charged carboxylate groups, it becomes more favorable to have sodium ions present. I'm not showing a completely sort of balanced situation here. What we're communicating is that if you were to add water to this polymer, some of the sodium atoms might, or ions might, be able to diffuse away. But the presence of so many negative charges in close proximity increases the favorability of having sodium ions stay nearby. Okay? So in the same way that distance between charges influences their interaction in an attractive fashion, that happens also repulsive. And so to have these negative charges close to each other, constrained by the covalent bonds, that increases their potential energy. It introduces a repulsive interaction. It makes it even more favorable for sodium to hang out. By the way, sodium polyacrylate is the major component of diapers. It absorbs, it's the super absorbent material that absorbs water, and that also has to do, its propensity to absorb water has to do with this kind of structure too. So we would say that there are, in a weak electrolyte, there are many ion pairs, because whatever the medium is, it's not strong enough to overcome all of the interactions. Another time that you will see ion pairs in biology will be with nucleic acids and their derivatives. I'm gonna draw like ATP or something like that. Polyanion. Here's the ribose ring. Oh great, now I'm on the spot. Can I draw the purine adenine? Maybe. I think so. Maybe. Anyway, this is ATP. You have, similar to polyacrylate, you have a bunch of negative charges in proximity, and it's thought that magnesium often acts as a chelator for often ion pairs with these phosphate groups. You will sometimes see people write that in, draw that explicitly in biochemical textbooks. Other times you just sort of assume it's present. But if you see a molecule of ATP, likely there's magnesium going along with it to help neutralize the charges. Yeah.
Can magnesium chelate with these other two?
Mm-hmm. Yeah, for sure. I don't know the extent to which either of these options is more favorable than the other, but yeah. And in some cases, it's only the presence of magnesium that allows chemistry to happen. We were talking about terpene chemistry, and I abbreviated the pyrophosphate group, but what it is this, 3 negative charges. And if it leaves, it would have 4, which, starting to be kind of maybe a problem. So likely what allows this to happen, what allows it to leave, is the fact that it's already chelated by magnesium. And that makes it easier for the group to leave. All right. Questions so far? So I'm a protein and peptide chemist, and so we call ion pairs within proteins and peptides salt bridges. And so just briefly, we'll talk about the kinds of cations and anions that are present in biology. Because biology occurs in water and in a relatively polar environment, you might expect the strength of interactions between charges to vary a lot depending on the situation. For example, you've got, maybe we're going to talk about that in a minute. Here are the cations that are typically present in proteins. The lysine side chain has an ammonium group. The arginine side chain has this group, which is called guanidinium. It's a planar cation, and by resonance you can actually delocalize that plus charge to each of those nitrogens. The negatively charged side chains are aspartate and glutamate. They just differ in the presence of a additional methylene group in glutamate. But based on Coulomb's law, remember Q1, Q2, 4 pi epsilon, permittivity, and R. Based on the distance between charges and the dielectric constant of the space between the two charges, you can expect that interaction to be stronger or weaker. So it's thought, for example, that if this is your Pac-Man protein, I'm sorry, it's a terrible drawing of a protein, but at least I didn't give it an acronym name, right? That was one of the things that frustrated me when I took biochemistry, was how everything had some unintelligible acronym name. But actually organic molecules are not that much better. Because once they get complicated, we just stop saying their names and call them compound 1, compound 2, and so on. All right, so here's your protein. This is area outside the protein is a polar environment. It's got lots of water. The area inside the protein is relatively nonpolar. So a salt bridge on the surface of a protein, an ion pair on the surface of a protein, is going to experience the full dielectric constant of water, and the interaction might not be that strong. You can do various experiments, and we'll talk about them in just a second, and it's about 0 to 2 kilocalories per mole, and usually pretty weak. However, if you're in the interior, nonpolar interior of a protein, the dielectric constant starts to go down. You become much closer to a vacuum. And you can see that if we just look here. Remember, the nonpolarist environments, hexane, benzene, have substantially lower dielectric constants than water. And so you would predict that the interaction energy between two charges in a protein interior are much stronger, and experiments verify this. So this is, do I dare talk about this? This is my research, so I don't know if it's that important to talk about, but why not? Sorry. So one of the things we do when assessing salt bridge strength is we individually change each of these side chains to a non-interacting surrogate. So a good amino acid that's often used is called alanine. And this technique is called alanine mutagenesis. In other words, you will take a lysine positive charge. Suppose this lysine is paired with this aspartate, and we want to know if that interaction is significant. We first replace the lysine with alanine. That gets rid of the interaction, but it also changes lysine to alanine. Then we do it the other way. We take aspartate and we change it to alanine. That also gets rid of the interaction, but it also has the effect of mutating aspartate to alanine, and so we do a final control, and that is mutating both of them to alanine. And when we compare the 4 different variants that we've looked at, that's called a double mutant cycle, we can extract, just by subtraction, the energy of the interaction. So what I'm showing you here is work that we did a few years ago in a paper in ACS Chemical Biology. The reference is boring and doesn't matter. Anyway, I just want to erase that so that we can see. All right, so we were working with a helical peptide that's called a coiled coil. We may have occasion to talk about that later. This involves two helices sort of wrapping around each other, and the nonpolar surface of the helix is on the inside, and then the exterior is often filled with charged residues. And we looked at, and in many cases, these charged residues, at least in crystal structures, appear to be involved in ion pairs. So as an example here, you have a glutamate residue that's very close to a lysine residue. And so what we did to determine the strength of that interaction, to see whether it was important or not, is we changed each of these amino acids from individually and then in combination to alanine, and then we could get a measure of salt bridge strength. But we were interested in the impact, interested in how context dependent the salt bridge strength might be. So nearby these salt bridges, we incorporated a polymer. This polymer is called polyethylene glycol, or PEG. We attached it to a nearby amino acid side chain. This PEG is not, I mean, it sort of has dual character. Because of the methylene groups, it's reasonably comfortable in nonpolar environments, but because of the oxygens, it's pretty comfortable in polar environments. It interacts really well with water. We wondered, we had evidence based on previous work that PEG might tend to remove water from the protein surface simply by taking up space, and so we wondered if having PEG nearby might shield these charges from water, thereby lowering the dielectric constant and increasing the strength of the interaction. And the answer is that sometimes it works and sometimes it doesn't. We found a couple of cases where having a nearby PEG dramatically increased the strength of a salt bridge. This arginine and this glutamate, the interaction got stronger by about 0.7 kilocalories per mole when you incorporated PEG here. A similar change here, but then there were other positions where it didn't work, and we're still sort of mulling that over.
So what are you currently thinking is happening then that's making it work sometimes and not work others?
Yeah, I mean, so you could do a number of things to tease that out. These are all crystal structures, and we don't have actual structures of variance with and without PEG. So it is possible that that if you put PEG here, it looks like it would be sort of oriented near these side chains, but actually proteins are pretty flexible. PEGs are too. And so it's possible that in this particular context, the PEG-elated side chain doesn't actually cover the nearby charges. In contrast, it's possible that other places it's better. One of the things we could do to try to figure that out would either be to get a crystal structure where we could see PEG, or to do some molecular dynamics simulations. So one of my students actually took the variant where we put PEG here and then tried to shield these two charges from each other. And this is the structure of the protein without PEG. So here's the positively charged side chain, here's the negatively charged side chain, and here's the site where we incorporated PEG. The gray mesh is electron density. So when you solve a crystal structure, and I know next to nothing about this, there's you try to, what crystallography, X-ray diffraction actually shows you is not where the atoms are, but where the electron density is. And so based on that, you can model the positions of the atoms. And so in gray, you're just seeing electron density contoured at a certain probability, and then we fit side chains and structures into that. This is the non-pegylated protein, and in crystal structures, often one protein will be packed pretty closely against another. And so you start to see some of that up here. Presumably the space between them is not a vacuum, but rather is filled with water molecules, but their freedom must be such that you don't see them in the diffraction experiment. If water molecules are moving quite rapidly, then they won't diffract X-rays, and you won't see them in the X-ray structure. Here is the pegylated variant, and again, here are the two side chains. There's a lot more electron density in this space. We tried to fit a model of a PEG polymer into some of this, but we're not able to do so in a way that explained all of it. And what we think is happening is that there's just multiple conformations, but that it's possible that in this case PEG is sort of in the area around the two charges, and that might explain the effect that we saw. So our tentative conclusion is, what does PEG do? I really wish, well, it was kind of fun, but the idea is that PEG maybe takes up space near the protein and removes water molecules, thereby shielding nearby interactions. And there's a fair amount of evidence that we're accumulating that can occur. I can't remember who encouraged me to do this. It was either my grad student Chung Xiao or perhaps Stephen Draper, but we turned asparagine into a cowboy that's using a whip to remove water molecules. I see that now and I'm like, we will never do that again. But it was fun in the moment. We've done some other things with salt bridges, but this story is even more complicated, so I won't tell it to you. Anyway, right.
Right.
Yes.
The energy equation where there's an energy equation where you have just one epsilon. What situation? Because I see something is like 4 pi E dot R.
Right. So there's sort of two other ways that you could see this. One would be to write Q1, Q2, 4 pi epsilon with a 0 and then R. That's for in a vacuum. So if you've taken a physics class, that's most likely the form that you've seen it in. If instead you want to say, okay, let's have this be in some medium, I'm not sure what the symbol would be used at, but if this is the epsilon for some medium, which I don't know what we'll call it, medium X or something like that, you could see just that, or you could see it this way where it's the vacuum and then the influence of the solvent. Alternatively, sometimes you don't even see this, and some people will write it as K, Q1, Q2 over R, and just incorporate all of these constants into the K, and that's fine too. Did that answer your question,
Yes.
sort of? Okay. All right. So that's probably enough about charges. And in terms of these non-covalent interactions, it's sort of mix and match. So what do I mean by that? You've got a couple of different options for non-zero charges, right? You can have the point charge, which we're going to call an ion. Then you've got the dipole, which is a linear distribution of charge. For example, a dipole would be if you have some negative charge here and some positive charge here, and they're constrained relative to each other. Usually dipoles don't involve full charges. Usually this is a partial positive charge here and a partial negative charge there. Classic example of this would be say, formaldehyde, where carbon is more electronegative than oxygen, and so you expect the carbon to be electron poor and the oxygen to be electron rich, and we could draw that dipole just aligned with the carbon-oxygen bond with the plus end of the dipole near the carbon. So that's like a linear distribution of electron density. And then there's another one called, and this is not that fun, quadrupole. And a quadrupole arises in a situation where, so sodium would be like an ion. A quadrupole arises in a situation where you have a non-uniform distribution of electron density in 3D space. So point, line, and then 3 dimensions here. The best way to talk about it, I think, is just with an example. So if you look at benzene, and we go up and look at benzene's dielectric constant, if I recall, it was like 4. So benzene is pretty dang nonpolar. Actually, it's 2. So benzene is just as nonpolar as hexane, all right? And of course, you could predict that it should have no dipole because it's perfectly symmetric, right? And so the carbon-hydrogen bond here, dipole associated with that one, because carbon and hydrogen electronegativities are not the same. Well, in fact, sp2 hybridized carbons are more electronegative than hydrogen. And so it's true that each of these individual bonds you could draw sort of a bond dipole, but they're all going to cancel each other out because of the symmetry of the molecule and the fact that the dipoles are all opposite to each other. Nevertheless, look at that. It's the carbons that are electron poor. Oh my gosh, I drew the dipoles in the wrong direction. How long were you going to let me do that? Very, very sorry. If carbon is more electronegative, the delta minus end of our dipole should be on the carbon. I'm very sorry for that. Oops, I'm also very sorry for that. I've done everything I know how to do to stop the thing from blanking out on the screen, but there we go. I mean, it's plugged in, it shouldn't go to sleep. All right, that's better, right? Did we fix that? Okay, so all of these dipoles offset each other by the one opposite, but all of the carbons are electron rich and all of the hydrogens are electron poor. So let's use a color red for electron richness. Sorry. Maybe a little bit. There we go. And then let's use the color maybe blue for electron poorness. And if you look at the benzene ring from the side, basically what you conclude is that the benzene ring has an electron poor edge but electron rich faces. And so sometimes people try to represent this by sort of making Saturn. There's the ring, there's an electron poor face on, a rich face on top, and an electron poor, sorry. An electron-rich face on top, an electron-rich face on the bottom, and then an electron-poor edge. So benzene is not polar, but it is quadrupolar. in the sense that the surface of benzene is not uniform in its electron density. And so you take these three different elements, three different distributions of charge, and you can mix and match them. For example, ion with itself is an ion pair. Ion with a dipole, we call that an ion-dipole interaction. And if it involves hydrogen, we say it involves hydrogen bonding to an ion. Two dipoles, we call that a dipole-dipole interaction. And if it involves hydrogen, we'll call it a hydrogen bond. Ion with a quadrupole, that starts to get a little bit exotic, but actually that's found all over the place in nature, and it's called a cation-pi interaction, because the positively charged ion can interact with the electron-rich face of the benzene ring. Alternatively, you could have an anion interact with the electron-poor edge of the ring, and that's also found all over in nature. You can have dipoles interact with quadrupoles, and we've seen some examples of that in my lab. All of these interactions are distance dependent, though the distance dependence changes, right? So we might say, if we're going to mix and match these, the ion-ion interaction, because they're points, it only depends on the strength of the interaction, only depends on 1/r, the distance between the two charges. If you've got an ion-dipole interaction, then distance and orientation does matter. And there are equations that the book presents, but you don't need to know them. You've got the distance between the charge and the dipole, and then you also have this angle between the charge and the dipole, and we won't worry about that particular law, but for iron dipole interactions, they vary, the energy varies with 1/r squared. What does that mean? That means it falls off faster with distance, right? With a 1/r dependence from Coulomb's law between ions, the larger the radius, the lower the interaction. But this now has radius squared, so that means that if you double the radius, you lower the interaction by a factor of 4, right? And this is actually general as you start to decrease the strength of the interactions. If you go dipole-dipole, the interaction is a 1/r to the 3. And then the distance dependencies for quadrupoles are not simple, because now you have to worry about 3D space. The orientation between a point and a line is pretty easy to describe, but now if I'm talking about a benzene ring, not only is distance from the ring important, but also where I am. Am I on this side, that side? Am I near the edge? And people have characterized those interactions, but there's not a simple law that we can write. Okay, so I want to talk about hydrogen bonding now, because that's one of the most famousest of the interactions. Some texts will write hydrogen bonding as its own thing, but hydrogen bonding could be an example of either the ion dipole or the dipole interactions. Okay. So the hydrogen bond, well, let me just draw a few examples of hydrogen bonds. So if you had HF interacting with some nitrile, you've got the electron-rich nitrogen, you've got an electron-rich fluorine, and you've got an electron-poor hydrogen. So, and that's the interaction. The language used here sometimes is a little bit backwards, and I always get confused on it. Because in some ways, a hydrogen bond is just a nucleophile-electrophile interaction, right? you could think of the electrons on the nitrogen donating partially into the hydrogen fluorine sigma star. So yeah, electron donor, electron acceptor, Lewis base, Lewis acid, Bronsted acid, Bronsted base. But we will nonetheless use the word hydrogen bond donor to describe the group that has the hydrogen attached to it that's going to participate in the hydrogen bond, and we'll call this a hydrogen bond acceptor. And that I always have to pause and think before I get, it's that and inter and intramolecular I always get wrong. I always have to pause and think before I say, because my natural inclination is to use donor and acceptor in the electron density Lewis acid, Lewis base way. All right, so because hydrogen bonds are so common, we want to spend a little bit of time talking about their strength and what experiments have been done to try to determine strength of hydrogen bonds, and also where they show up in nature. So I'm going to show you some research from my PhD advisor. This is his early work. This was done about the time that Paul Savage was in Gelman's lab. Paul did his PhD in Gelman's lab and graduated in the early 90s, and then I did mine in Gelman's lab and graduated in 2008. So we are PhD brothers, but he is my much older PhD brother. Don't tell him I said that. He's not actually, Paul, you're not actually much older. Paul's a great mentor, and I've admired him. In fact, the fact that he did his PhD in Professor Gelman's lab made it easier for me to do mine in that lab, because Paul was a Latter-day Saint, and he wanted to be able to spend time with his family and do research, and he basically showed Professor Gelman that that was possible. So by the time I joined Professor Gelman's group, he was totally used to having Latter-day Saints in his lab, and with them having children and needing to go home at night and all of that stuff. So anyway.
You didn't know him before that time?
I didn't know who?
Dr. Paul Savage.
Let's see. No, I met Paul Savage here. He taught me before I went to Wisconsin. So I can't remember when Paul graduated here, but he did his PhD in Sam Gelman's lab at the University of Wisconsin. But at the time, he was one of Sam's first graduate students. And if you join a lab with an assistant professor, their job is to discover something awesome and get tenure, and so they expect their students to be working a lot. Sam's preference, Professor Gelman's preference, was for students to work during the day and then go home for dinner and then come back afterwards and stay till, however long it took. And so ideally, Gelman would have preferred students to be working 70 or 80 hours a week, and Paul was like, I'm married, I have kids, I'm not coming back at night. And at first I think Professor Gelman didn't like that, but Paul was so productive during the day that he demonstrated, hey, just let me do my thing, right? And as long as Paul was producing results and taking his project forward, Professor Gelman was happy. And so then he had a few other Latter-day Saint students. So Matt Wall, Dr. Matt Wall, who came and gave a seminar a week or so ago, was one of Gelman's students when I joined his group. There was another Latter-day Saint there as well, and then me. By the time I came along, Sam Gelman was totally unsurprised when, a Latter-day Saint grad student would have a child and need to and have family obligations. So anyway, it's interesting. Sorry, that's a huge detour. We talked about student ratings. One of the things that people say is that I get easily derailed to tell stories, and some people like it and some people don't. Anyway, this is a molecule Professor Gelman studied, And he designed this molecule that could form a 9-membered hydrogen-bound ring with minimal torsional strain. And he was able to measure the presence of this hydrogen bond via a simple infrared spectroscopy experiment, because you can detect amide protons very easily in the IR, and their the shape of the peak and where its particular wave number varies if it's hydrogen bound or not. And so they were able to increase temperature and sort of try to calculate how strong the hydrogen bond was. They did the experiment in chloroform, and they found, and the numbers aren't necessarily important, but interaction strength is often assessed in enthalpy, and they measured that it was worth about minus 1.4 to 1.6 kilocalories per mole. And again, remember the number I told you to remember. That's worth about a factor of 10 in equilibrium constant. Now, that number is in chloroform, not in water, and we'll need to talk next time about what solvent would do to that situation. All right, have a good weekend. I will grade your exams. I will put the scores in Learning Suite, and then you can come pick up the exam and look at it anytime. I'll also post the key in Learning Suite.
Dr. Price, what is the optimal distance of a hydrogen bond?
What is the optimal distance of a hydrogen bond? Good question. Often from crystal structures, you can tell that a hydrogen bond is strong if this atom and the hydrogen are closer together than the sum of their van der Waals radii. And that indicates that there's some, hydrogen bonds are strong enough that you reason that there's some sort of partial covalent character. We're talking 3 or 4 angstroms between oxygen and nitrogen, and then you'd say that was probably a hydrogen bond.
Formula for chloroform.
Oh, that's not chloroform. Sorry.
So
This
CH2Cl3. Yeah, this is correct. It was dichloromethane.
So approximately 2.5 angstroms
Between,
the hydrogen and the oxygen.
I'll need to look that up. That's a good question. I'll see if I can find that out.
I have a structural diagram.
So it will
It's
be-
about half an hour.
Oh, okay.
That's why I'm wondering.
Okay. Let's, we can Google that
So it was
actually.
done in this, not